Welcome to the mean value theorem, chapter 5, section 2a. This is going to be another important one for us. There's a lot of meaty problems in this section as well as in section 2, in section 5.1. The mean value theorem for derivatives. This is one that's going to make sense after we talk through it, but it's going to have a lot of little spin-offs and corollaries that are going to be really useful for us in evaluating functions. So the mean value theorem says if we have a height equal to f of x, if it's continuous at every point of the closed interval a to b, continuous, we can't lift our pencil, and differentiable, smooth and never infinite, the curve never becomes completely straight up and down at any instant. Then, and that's on the interior from a to b, then there's at least one point c from a to b in which f prime c equals fb minus f of a all on b minus a. And there's a lot going on there, but I think this is going to make a lot of sense to us. Now, hopefully, we recognize instantly that this is a slope. This is a y value minus a y value over an x value minus an x value, but not just that, it's a height at x equals b minus a height at x equals a all on a. And of course, f prime, the derivative of f, is a slope. So this should make perfect sense to us if we understand that. Let's take a look at a picture. Maybe this will help with the understanding. So here I've got just some arbitrary function. It is most clearly closed, or it's most clearly closed from a to b. It's also most clearly continuous. Didn't lift the pencil, and appears as though every point is differentiable. We've got a smooth curve along the way, provided I drew it well. Therefore, mean value theorem, the hypothesis is satisfied. But let's take a look at what this says. This is saying I want the height at b minus the height at a over b minus a. That is just y minus y over x minus x, the change of y over change of x. It's finding the slope from this point to that point. It's finding the slope of that secant line. And the hypothesis, with the hypothesis met, the mean value theorem says that therefore there must be some slope somewhere on this curve that matches up to that. And we can pretty well see that somewhere along here there would be a tangent line. And somewhere along here there would be a tangent line that would appear to be parallel to that tangent line. So what's up with the whole differentiable? What difference does that make? Well, let's say I had a curve from a to b that looked like that. That's still on the closed interval. It's still continuous, didn't lift the pen. However, not differentiable, and if you look, it's hard to find a spot where it looks like the slope of the green curve is equal to the slope of my secant line. Okay, so we have to make sure we meet those hypotheses before we apply the mean value theorem. Okay, some things that spin off of it. Well, actually, increasing and decreasing function, this is old review, but we're going to have another way of looking at increasing and decreasing functions because of the mean value theorem. Functions increasing and decreasing, this should make perfect sense to us. Says that a function f increases on some interval, x1 and x2, it can be any 2 points on it. If x1 is to the left of x2, then any point that's to the left of another point, the height is lower. So if I've got a point to the left of another point, this has to be lower than that. Well, of course, that's an increasing function. Then likewise, if any point is to the left of another, if that implies that the height to the left is bigger than the height to the right, and that's for any and all points, then the function is decreasing on that interval. Okay, so that is old news. That is pre-calculus, perhaps even some algebra 2. But here is a corollary that spins off of mean value theorem, increasing and decreasing functions, and kind of in combination with this. It says let f be a continuous function from a to b and differentiable on the interval a to b. We need to learn to make certain we're reading that as an interval and not as an ordered pair point. Then, if the derivative is greater than 0 at each point on the interval from a to b, then f increases on that interval. Well, that should make perfect sense as well, because this is saying if the slope is positive from point A to point B, then the graph is going up. If the slope is negative from point A to B, from any points A to B, at each point from A to B, then we have to be going down. Okay, makes sense completely. So will this one, corollary 2, functions where the slope is 0, not f prime is 0, let's put some meaning to it. If the slope is 0 at each point, if the slope's 0 from here to here and here to here and every point on there, what kind of graph, what kind of function would that be? This might be something like, here's my axis, this might be like y equals 2. It's a constant. No big deal. All right, and functions with the same derivative differ by a constant. Okay, so that's kind of an interesting one. That says, well, let's look at this one. 3x cubed minus 2x plus 4 and 3x cubed minus 2x plus 11. We quickly see those have the same derivative, 9x squared minus 2, but they are clearly not the same function. To look at a picture of that, here I've attempted to draw two identical functions other than g is four steps above f. We might say that g of x equals f of x plus 4. Now, if you look at this, any corresponding point, for instance, this one right here, if I drew this correctly, would have the same slope from function to function, if this was just a stamp of that. So what it's saying is we can get the same derivative a lot of different ways. The derivative of sine of x is the same as the derivative of sine of x minus 70. Slopes are the same at corresponding values of x. So that's what that tells us. And then we introduce this concept of an antiderivative, which, if you haven't heard the word before, it's exactly what you would expect it to be. For instance, we know that 4x cubed's derivative is 12x squared. However, we also know that 4x cubed plus 11's derivative, first derivative, is 12x squared. The antiderivative, and we'll talk about notation of this a lot as we come up, but right now I'm just going to say the antiderivative of 12x squared is 4x cubed. However, because this and this gave me the same derivative, the antiderivative has to assume that perhaps there's some constant added on, and it would just be listed as plus c. And you say, well, could it be minus c? Well, no, we'll just call it plus c because, of course, c could be a negative number. Okay, let's start applying some of this. Example 1, state whether or not the function satisfies the hypothesis of the mean value theorem. So do we remember what it is? Has to be a continuous curve, has to be differentiable at all points. If so, then here's our formula that applies. It says somewhere along the curve, the slope of it has to equal the slope of the starting point to the ending point. Well, we know about this graph. We know that this is a parabola. Polynomial graphs are always continuous, are always differentiable. So the mean value theorem for derivatives, the mean value theorem, hypothesis is met. It is continuous and differentiable at all points from 0 to 1. Okay, so that means that we can now say that there must exist, here's f prime of x, there must exist some value c, or f prime of c, 2c plus 2, where the slope is the same as this formula. Okay, so I need to find f of a. F of a is 0, our starting point, 0 squared plus 2 times 0 minus 1, or negative 1. F of b is 1 squared plus 2 times 1 minus 1, or 3 minus 1, 2. So f of 1, or f of b minus, we could put it that way, or with 1, minus f of a on b minus a is 2 minus negative 1 on 1 minus 0, or we get 3. And the formula says that this should equal this. So 2c plus 2 equals 3 when c equals, subtract 2, 1, divide 1/2. Now, not only can we find a value of c, but that value of c has to be on that interval, and it is. So something to note as we move forward with this, let's say that our derivative ended up with a cubic and we found 3 different places where c was, or 3 different values for c here. We'd have to go back and make sure that we're looking on it's the one that fits in that interval, but clearly 1/2 fits between 0 and a 1. Okay, B. This is a continuous curve. I don't have to pick up my pencil to draw this curve from -1 to 1, so half of the mean value hypothesis is met. I just have to figure out if it's differentiable at all points. I can take a third root of negatives, I can take a third root of 0, I can take a third root of 1, I can take a third root of anything along the way. So let's find our derivative. F prime of x equals 1/3 x to the negative 2/3, or -1 on 3 third root of x squared. I can square any number I want. I can take the third root of any number I want. I can multiply 3 by any number I want, but I cannot divide by any number I want. X cannot equal 0, therefore this is non-differentiable at a point on the interval. If this just said from 1 to 6, we'd have no problem, but -1 to 1, it's non-differentiable. Therefore, the mean value theorem, I should say, I'm going to say does not apply, but I'm going to say hypothesis is not met, and that's what they said. If it does not meet it, we don't have to use that. We really can't use it. Doesn't mean if we went through it that it might not work. There still might be a point on there where the slope is the same, but the mean value hypothesis was not met. Okay, example 2. This is a pretty simple real world problem involving mean value theorem, but we'll be building off of this type of idea. A trucker handed in a ticket at a toll booth showing that in 2 hours she had covered 159 miles on a toll road with a speed limit of 65 miles per hour. Well, this is just our average rate of change right here. So our average rate of change is covered 159 miles in 2 hours. That is 79.5 miles per hour. And it quickly stands to reason that at some point this driver was probably driving over 79.5 unless she was constantly driving 79.5. And that is the mean value theorem. The mean value theorem guarantees at some point along the line she had to be driving at least 79.5 miles per hour. And she'd probably be getting off easy at 79.5 speeding ticket, because chances are at some point she was going faster. Now, does the mean value theorem really apply to this? Well, her speed would never change from, say, let's say she's going 60. She wouldn't hit the accelerator and instantly be going 64. It would be a gradual, smooth change of speed. And if it's gradual, smooth, and continuous, it would be differentiable. Therefore, the trucker was cited for speeding. Let's see. The mean value theorem tells us at some point she had to be traveling at 79.5 miles per hour. Maybe just for an instant, and then she went faster, slower, but at some point she had to be traveling at 79.5 miles per hour, therefore justified to give a speeding ticket at that value. Alrighty, now the directions here are going to seem very, very similar to what we were doing in 5.1. The big part of this is we have one trick up our sleeve here that we really haven't talked too much about, and that is when we're talking about increasing and decreasing functions, and it helps to figure out when they're increasing to a maximum or minimum. Maybe instead of just considering the point, consider the slope leading into that point. Is it positive? Is it negative? That tells us about increasing and decreasing functions. So we're going to probably spend a little bit more time on some of these analyzing slopes. Use analytic methods to find the extrema. So I'm going to put A. The extrema. B. Increasing. Intervals. We're going to use interval notation. We're not going to say X is greater than. We're going to use interval notation. Increasing. C. Decreasing. I really want to stress that's a good habit for you to get into when you're asked multiple parts for your answer. It's easy to find something and move on. We've been conditioned too often in mathematics that once we find a solution, we move on to the next problem. Okay, continuous, never lift the pencil, differentiable, it's a polynomial. In fact, we know this thing has n-model behavior. It's an upside down parabola. It wants to fall to the right. It wants to fall to the left. Therefore, we probably have an extreme value. It's going to be a max. We're not going to have any minimums. So let's find our derivative. F prime x is 5x. No, it's not. It's 5 minus 2x. And we want to know two things about that for extremes. We want to know when is the slope 0, and we want to know when is it non-differentiable. Well, the slope is 0 when 5 minus 2x equals 0, or when x equals 5 halves. It's always differentiable. So the only value where we can have an extreme is at 5 halves. F of 5 halves gives me 5 times 5 halves minus 5 halves squared, or 25 halves minus 25 fourths, 25 fourths. So I believe, knowing this, I am certain, I don't just believe, I'm certain that we have a maximum, an absolute maximum of 25 fourths at x equals 5 halves, and that's the only one we have. Now again, because I know what this graph looks like, I know it's increasing prior to getting to a value of 5 halves and decreasing afterwards. However, I could come back and make this little chart, which we're going to be doing a lot of. I'm just going to call this is the chart of the signs of the derivative. At 5 halves, our derivative is 0. If I put a value bigger than 5 halves, like 3, if I put 3 in here, I get 5 minus 6, it's negative. If I put a value prior to here, prior to 5 halves, like 0, I get 5, it's positive, which means the graph is increasing to the point where the slope is 0, and then it's decreasing. Therefore, we have an increasing function on the interval negative infinity to 5 halves. Is it increasing at 5 halves? No. Parenthesis. Then it's decreasing from the other side of 5 halves to infinity. Okay, so let's organize. Let's make certain we're leaving space and we're answering all the questions asked. All right, B. Again, they're not asking does the mean value theorem apply here, because we might have some problems here. This is not a continuous function, isn't continuous at 0, but they're just asking for, again, A, our extrema, B, intervals of increasing, and C, decreasing intervals. And let's take a look. First derivative would be, if I treat this as 2x to the negative first, I can just go negative 2x to the negative second, or negative 2 on x squared. and I want points where the slope is 0, and I want points of non-differentiability. Well, the slope is 0 when -2 equals 0. When the numerator is 0, never. And it's non-differentiable when x is 0. We can't divide by 0. We can square anything at x equals 0. But x equals 0 doesn't exist on this graph, so it doesn't give us a whole lot to go on. Okay, so if this is our slope, -2 on x squared, other than our point of non-differentiability, what do we know about the slope of this? So here is h prime at 0. We have an undefined slope. How about to the right of 0, it's positive. To the left of, to the right of 0, it's negative divided by positive, negative. To the left of 0, it's negative divided by positive, negative. We have a function that decreases everywhere but doesn't exist at 0. This function is decreasing from -infinity to 0 in union with 0 to infinity. It is never increasing. And if it's decreasing all the time where it's differentiable, then we have no extremes. And we never even had to create a graph of that would show us that we had a graph like this. Notice, decreasing all the time, decreasing all the time. Even though it jumps from down here to up there, the curve is constantly decreasing, except at 0. Okay, so these little charts are going to become a big player in what we're doing moving forward in this section. I'm going to pause this video and we will come back to it. Thanks for watching.